But now we have Pablo Marchant and Guillaume. Is that right? We'll introduce Pablo. Your name, Guillaume. Jaime.
Yes, senor. Yes. Well, it's my great pleasure to introduce today's hijack speaker, Dr. Pablo Marchant. So Pablo is going to be here for the rest of the week. From tomorrow, he will be at MPIA. If you want to have a chat with him, let us know. So Pablo is an assistant professor at Ghent University. This is a position that he just currently took early this year, that's correct, after spending quite a bit of time at KU Leuven, where he was a FWO fellow, both junior and senior. So was that 6 years in total that he spent at KU Leuven? And before that, he was a postdoc at Northwestern University at Sierra, which came after his PhD in Potsdam.
Bonn.
Sorry, Bonn. That's why you do this.
You almost got it.
So his work centers essentially on the evolution of massive binary stars and the pathways that lead these objects to gravitational wave sources, right? So Pablo's large contributions to the field were just recognized last year when he obtained an ERC starting grant for the project Star Grasp, which aimed at linking theoretical modeling to currently and upcoming observations of gravitational waves. So also important to mention, during his stay at MPIA, he will also give the COCO, the Koenig-Stuhl Colloquium, on Friday, in case you want to join us. The topic there will be a little bit more focused on black holes. Is that correct? Yes, so if you want to hear about that, don't miss it. So please join me in giving a welcome to Heidelberg.
Yep. So thanks for that, Jaime. There were some technical issues, so maybe something will happen in the middle of the presentation. Hopefully not. Let's see how this goes. So yeah, I wanted to talk today. I work a lot with black holes, gravitational wave sources, but today I wanted to talk about less extreme objects, just talking about mass transfer, the formation of strip stars, and how, for many cases, I like massive stars, but we don't always need to go all the way to very massive stars to understand physics. But just to motivate things, I wasn't quite aware what the audience for this would be, whether or not all of you know about stellar astrophysics. So I just wanted to start a talk on binary stars, talking about some fun binary systems, some exotic stuff that is out there. So just to start with one example. This one over here is a naked eye star that we can see. It's called Algol. And this is a pair of binary stars that go around each other in a very short period orbit. So the thing is that these systems are pretty much characterized by strong interactions. These stars do not evolve as single stars. They are defined by the way they go along each other. So the term that was coined for this system was the Algol paradox. So the main thing was that the less evolved star that we see in here, it's a 0.7 solar mass star that essentially for it to evolve, it needs the entire lifetime of the universe. It's actually much more evolved than its companion, which is 3 solar masses. So the question is, how do you do this? And the way that this was worked out was through mass transfer. So this is kind of one of these exotic systems where we need to think beyond single star evolution to understand them. Now, going a bit forward, we're still talking about things that are quite old in general, at least within my generation. So blue straggler. So people started looking at HR diagrams, color magnitude diagrams of single populations, single clusters. And what you would usually see in these circumstances is what you would expect. So you'd have nice main sequence that should not appear yet. Hertzsprung gap, red giants over here, horizontal branch stars. But then every time you see a population like this, these guys come over here. So these are stars that are more luminous and blue than the turn-off point, and they were coined essentially as blue stragglers by Burbidge and Sandage. So again, how can this be? So if we have a coeval population, we shouldn't be producing this. Again, the answer to this is some form of mass transfer, some form of rejuvenation, where a star that was lower mass initially gets more mass, so it appears as an older star. Yet more examples of exotic stuff like this. X-ray binaries. So the beginning of X-ray astronomy was essentially putting these things into rockets. So Giacconi was really the pioneer on this. The objective of this instrument was to observe X-rays reflecting from the moon, reflecting from X-rays from the sun, reflecting from the moon. The outcome when they shoot it out, I think they essentially misfired a bit. It pointed into another direction, and what they saw was this. They saw an X-ray binary. They saw Scorpius X1. So the first thing, the window of X-ray astronomy opens and they see a binary. So yeah, this is an exotic thing. There's a star, a neutron star there, accreting matter, emitting high energy radiation. So then I could keep going like this for ages, talking about weird stuff that's happening. Just want to mention one more, which is gravitational wave sources. So this is something much more recent, I would say. At least I felt young when this happened. So this is new window to the universe. We're seeing compact objects collide, and these are by nature binary systems. We have two remnants, two cores of stars that collapse into neutron stars and black holes, and produce this high frequency radiation that we're detecting directly right now. And this is a very exciting and growing field. We had about 100 detections, and these are increasing significantly. So by the end of this year, there should be quite more announced. We should go into the range of 400, 500. And really, there's a bit of an exponential increase as the range of these detectors keeps growing and growing. So I'm showing all this funny stuff. So then the question begs the question, like, are they really exotic? If we're seeing all this stuff that's doing all these funny things, are they really exotica? That's the term that was often used for them. I guess the question is that not really. So the way we can go and test this is just by observing stars. We go out there, we measure a lot of systems with particular observation methods that can allow us to infer if there's a binary there or not. So this is just a figure by Uksana that's summarizing here at bottom, just different techniques that you can use to detect whether or not a system is a binary. So ignoring a bit here, binary formation, we have, for instance, photometry, where the shortest period binaries and often show variations being, be it, for instance, eclipsing binaries. Algol is an example of such a system. And spectroscopy, we can see the shifts in spectral lines, and this again gives us a measure of binary systems. We can see systems with two spectral lines that are moving back and forth in counterphase. And there's a whole bunch of other methods, but I in particular want to focus in spectroscopy, because if we look here at the top, where more or less in the x-axis, we're marking different physical separations that are being probed. This is the regime of what we call closed binary evolution. So these are systems that are sufficiently close together that as they grow, they will interact with each other, because otherwise we just have two single stars evolving by themselves. They're just far apart each other. They can be useful for mass measurements, for instance, but they're not exhibiting interesting behavior just by being binaries. So if we go towards a spectroscopic surveys, people that went out measured a lot of binaries in this way. This is a summary of different surveys carried out in the Milky Way. We have essentially the number of stars being sampled and a bunch of extra information like the spectral types, the age. This really focuses on massive stars, and it's part of a review I wrote together with Julia Bodensteiner. That's 2024. If that's always 2025, it's 2024. And what I want to point out is that for a while now, if we look, well, not that one. So if we look in here, for instance, we have here a survey from the 90s, here a survey from 87, so just a year after I was born. If they go out and say, okay, we detect all these binaries, and they see the fractions, it turns out this is 40%. This one over here is 35%. So people had a good idea that apparently binary evolution is not this weird thing. And then something that I think really closed the deal in the minds of people to understand that binary interaction is really, really common, particularly for massive binary stars, is what's going on in here. So this was the work of Uksana in 2012. And what they did in here is the exercise of, if we see a bunch of binary systems with a given survey that was designed in a specific way, how many systems are we missing due to systematics, due to maybe the inclination not being favorable, due to mass ratio being too extreme and things like that. And then they can correct and obtain what they call an intrinsic binary fraction. And what they see is that 70% of the massive stars we observe live in binaries. And this really means 70% of the points that have massive stars. So each of those points that are binary actually have 2 stars. So binary interaction is absolutely fundamental for massive star evolution. And this is kind of the emerging picture that comes out of this. I'll discuss a bit about these different outcomes, but what happens is that when we talk about, this is O stars in particular, it's about 30% of them that are what we call effectively single. Either that they're a single star or they're a wide enough binary that there's no interaction in them. So this kind of picture that we see in here, 2 massive stars. This is an illustration of a 30 plus 30 solar mass binary, over contact binary that is in the Large Magellanic Cloud. This is a common form of stellar evolution. So this, if we want to understand the larger impact of stars in the universe as a whole, we cannot escape from this and just care about single star evolution. And there's a lot of stuff stars do to the universe at large. So hot massive stars are a large source of ionizing radiation. They can play a role in cosmic ionization. They can release lots of material through their lifetimes in a bit of a more secular way through powerful stellar winds. But also in more or less as they reach the end stages of their lives, they can explode and populate the universe and drive a large part of galactic chemical evolution. Not all of it, some of it goes to lower mass stars as well, of course. So just a bit of an outline of the things I want to chat about. I want to give a brief overview on binary evolution, just a 101. Hope it's not too basic. And then I want to talk a bit about some new discoveries of binary interaction products and how this can inform some uncertainties in binary evolution theories. Next on, I want to go focus more on this and say how some of these discoveries constrain the specifics of mass transfer in binary systems, some physics that we're not sure how they go, and talk a bit about the future and some interesting things that are happening that are essentially both on theory and observations and going to provide us some exciting information. So let's get into binary evolution. So very basic in here, some nomenclature. When we're talking about binaries, something that's very useful, at least when we're thinking about circular binaries, is the Roche potential. So the Roche potential is an effective potential in a core-rotating frame that contains both what's the centrifugal force and the gravitational force of both stars. So if we are in equilibrium in the core-rotating frame, this defines well-defined like wells where a star would fit, and if it's well within its region, it wouldn't interact with its companion. So we can see that as a star grows within its own region, it eventually reaches a point where it overflows an inner point of this potential, what's called the first Lagrangian point. And in this situation, we will start to have mass spilling from one star to the other with significant deformation of this donor star. And we can keep going further. We can have these contact systems like I was showing before, where both stars go beyond, up to the point where we can overflow some of these outer points, at which point we expect significant instabilities to occur. So going a bit further, so these are different types of binaries. What are the scales at which binaries evolve? So the scales, the physical distance scales for binary evolution are mostly defined by the radii of stars. So this is just a simple example showing stellar evolution tracks for solar metallicity moles at 10, 20, 40 solar masses, just showing how the radius evolves compared to the time with respect to the time of the main sequence as normalizing factor. And we can see that stars can go from radii, massive stars from radii of a solar mass down to a solar radius down to 1,000 solar radius or more. We can turn this around with this concept of the Roche potential I was saying before. We have kind of these well-defined periods at which we'd expect a star with a certain radius and a certain companion to interact. So we can talk about the periods at which these stars would interact with different companions. So this gives us a bit of bands because it's somewhat dependent on the mass ratio, but still we can see that the interaction periods in here range from 1/10 of a day, so a few hours, all the way up to 1,000 days. So we're talking about the scale of a few years for things to interact and happen. So on top of this, it's important to understand that even if we have interaction happening, this is not necessarily the timescale at which a system will evolve. A star is essentially defined by its three fundamental timescales. We have dynamical timescale, thermal timescale, and nuclear timescale. These are very mass dependent. These are just your typical massive star numbers. So the dynamical timescale by construction is going to be on the order of the orbital period. But then we have this other thermal timescale on the order of thousands of years, and your nuclear timescale on the order of mega years. So we're going essentially from timescales of days, or even if we have very compact stars, it can be hours, all the way down to mega years. And this is something fundamental that places some restrictions on how we model stars. So if we want to model these stars just as fluids, throw them into a 3D hydrodynamics code and attempt to resolve the dynamical timescale and at the same time the nuclear timescale, it's a hopeless problem. So this is not something that we can hope, like Moore's law, even if it would still work, it's not going to give us a sort of tool that would allow us to cover this gap in timescales anytime soon. So two stars interact. What happens then? So we expect the orbit to evolve essentially as mass is passed from one star to the other. So again, this can be a very complex three-dimensional problem, but we can use some basic physics to establish what happens in this situation. So we can talk about the orbital angular momentum of the system. This is just the standard expression coming from Newtonian gravity. And just taking into account this property and how the masses of both stars evolve through a mass transfer phase, we can write some analytical expressions that say how this orbital separation evolves with respect to the mass ratio of the system. So as mass is passed from one star to the other, the mass ratio of the binary changes, and that can tell us more or less how the orbit evolves. So one thing that we don't know from this, though, we don't know the speed at which the orbit evolves. This is just saying how it evolves as mass changes. But also we don't know how conservative mass transfer is. So for reasons I will talk about later, we don't know if all the mass that goes from one star to the other is actually kept in the star. There are some important limitations that might come into play. So we can play this game doing this and considering, for instance, what happens if all the mass is conserved and retained or all the mass is ejected from the system instead. So checking the fully conservative line in here, what we see is that generally we expect evolution in this diagram to start on the left in here. The mass ratio is the mass of the accretor over the donor. Usually the more massive star is the one that will interact first. So we start from this left side. And what happens is that the orbital separation will usually shrink until the mass ratio is inverted, and then it will keep expanding with some slight variation if mass is fully non-conservative. Now, I want to point out that this, as I was saying, I'm more or less glossing over all this 3D hydrodynamics, but when 3D hydrodynamics becomes important, they can be very important. So we can have cases, for instance, when the star cannot adjust to the shrinking orbit, it might be happening too fast for things to adjust. It might just keep overflowing and overflowing and overflowing, and we end up with something like a merger. And these are some very nice simulations carried by Fabian Schneider, a local over here. Okay, so I've gone through all this, so I guess now you're ready to understand a diagram like this. So this is what we like to call a Van den Heuvel diagram from based on Ed van den Heuvel, who popularized with their use. And the idea is just all these interactions can be very different, and we just give names to all these different phases. So we have in here, we start with two main sequence stars, and there's a whole bunch of interaction phases, interaction happening in one direction, interaction happening in the other. There's branching points that can come out of this. And this is one particular case that can end up with a gravitational wave merger in the end. So there's a lot of uncertainties in all that happens in here. And like end-to-end modeling is very difficult to do. So I don't want to cover like 20 different phases of binary evolution today. So I'm just going to do it a bit simpler. Let's just talk about the first phase of stripping. We have two main sequence stars. At some point, the more massive one will evolve. It will develop a helium core, and then it will transfer mass. And usually the outcome of this is that you produce a star that's mostly composed of helium. It does have a bit of a hydrogen envelope on top. It doesn't fully get rid of that. These kind of stars are quite interesting in the sense that they can become very hot after stripping. They can go to temperatures above 50 kilokelvin, and that means they can produce significant ionizing radiation. So they can have an impact, a very important impact in the universe at large. The consequences for the companion star usually is that material that's transferred carries a significant amount of angular momentum, and they can be spun up to the point where they develop their own decretion disks, and observationally we call them B stars. That's kind of the observational counterpart to the theoretical description. So how do we mold the system? Just a brief mention on that. So I was saying that we cannot do this in 3D. We cannot mold these things in full 3D hydro. So actually we have 3 tiers in which binaries are evolved. So I would say there's the first one, the quickest one, which is rapid population synthesis. We have very simple molds that define how these interactions should happen, how mass transfers from one, how they evolve further. And these make very significant simplifications, but they have the benefit that molding a stellar system takes less than a second. Often, when we talk about stellar evolution, we want to mold populations. It's not enough to mold a single star. So this is very convenient to very quickly mold large groups of stars, modify some assumptions you're doing, and so on and so forth. The place where I work most is on the stellar structure and evolution field. So I was the developer within the MESA Stellar Evolution project. This is an open source tool that's really the most used tool for stellar structure and evolution. I took care of developing the binary evolution capabilities of this code. And this is something that we're really solving the equations of stellar structure and evolution in one dimension. This means that simulations take on the order of core hours rather than sub-seconds, so it's much more expensive to do, but the fidelity of the simulations is much larger. And I think we're moving to a regime where this fidelity is something we really need to have. Now I want to point out this diagram that's on the right. This is just what's called a keep and hand diagram, and this highlights the scenario I was showing before, where we have mass transfer, stripping a star and producing a more or less a stripped helium-rich object. So this is just showing cuts in the full mass profile of a star and molding at different ages. And you can see from the language that this is from Germany. This is from Rudolf Kippenhahn, which was really a pioneer on this kind of simulations. So this was also doing 1D stellar structure and evolution simulations of binary systems. And I can say, if I try to reproduce this, I will get a very similar result. So the methods to do this have been quite stable for a very long time and quite robust within a given set of assumptions that we take. So I think that really tells to the excellent work that these people were doing back then. And then, of course, I was saying 3D hydro is very hard if we want to model evolutionary timescales. But in the case where we have dynamical evolution, where we cannot get away from this, we really need 3D hydro codes. For instance, Arepo is one that's used here quite often. But then the simulations, depending on the detail you add, can be very expensive for a single system that you model. And again, if we want to model populations, we cannot rely on single simulations of events. So we need to find a good common ground to inform these 1D simulations with 3D simulations. Okay, so that was a bit theory of binary evolution and some details of how we do it. Now I want to go towards some new discoveries of binary interaction products. So this is, again, the year is wrong over there, that's 2024. This is a figure we produced out of this review that was showing a bunch of post-interaction products. So here we're not focusing so much in the star that's secreting material, we're focusing on the star that's losing material. So we have a bunch of tracks in the background that are showing stars of different masses that evolve in their main sequence, they expand, and eventually they interact with a companion. The details of that are not entirely important to this, but then they essentially, after losing their hydrogen envelopes, they contract significantly and produce a hot strip star. And there are various families of these strip stars that have been observed. Want to point some that are a bit more classical that have been known for quite a while. We have SDOs with B star companions here down at the lowest luminosities. All the way up there, we have Wolf-Rayet stars. This is just a small subset that's very clearly identified to be the product of binary evolution. But then we have all these other things that are quite recent. So we have some hot stars there filling a bit this gap. So a long-standing issue is that these stripping models can really produce hot stars that populate this entire luminosity range. But for a very long time, we've only observed those guys up there and this one's up there. So I want to go a bit more into details in this. And in particular, I'm going to start with this sample in here that says from Ilva Goldberg, 2023, which are all those points that are starting to fill this gap. So I'm just going to briefly mention these ones, which we call intermediate mass strip stars. They fill this gap between those very bright and stars with significant outflows, the Wolf-Rayet stars, and these SDO objects that are core helium burning objects that probably won't go beyond core helium burning. And the thing is that these stars are often very difficult to find because they don't have spectral features that scream at you like Wolf-Rayet stars do, large emission lines, very broad emission lines. And often they have stars that are bright in the optical, companions that are bright in the optical. So these stars are mostly brighter at high, and most of their flux is contained at higher frequencies. So that makes it very challenging to observe them with ground-based surveys. So what they did in here was really trying to identify systems that exhibit a blue excess in their colors, and talking in particular in UV colors. So they based this out of a very large catalog compiled by Bethany Ludwig. And then what's shown here on the left is more or less systems in the large Magellanic Cloud. There's the small Magellanic Cloud coming out of this survey, this catalog, I mean. And we can see where the main sequence lies out of this. And systems that lie to the left of this have an indication that there's something hot that's pushing them to where a single regular star would not be. So just by following this up with ground-based spectroscopy, they were able to clearly identify that many of these were actually strip stars. So moving a bit forward from that, there's a lot more that could be said, but I want to focus a bit on these systems over here that live in this intermediate regime where we have a bit of a degeneracy. We have main sequence stars that live at around these temperatures, but we also have these contracting post-interaction stars in the same region. So I want to start by putting one of these systems. So this was the kind of the discovery of one of these objects. So what they saw, they observed one of these systems, and they ended up determining that this is a 70 solar mass black hole that's contained in there. It was a very big because it broke a bunch of things we believed about stellar evolution. The most massive black hole that we saw in the galaxy to that point was about 20 solar masses. So then the question is, how is this even possible? So essentially the core of the process they did in here was that said, okay, we can measure the radial velocities of these two objects through spectroscopy. And then we see one of the stars, it looks like a very common B-type star. It has a large radial velocity variation and an 80-day period. And there's a bunch of H-alpha emission that's also moving in counter phase, but it has a much lower amplitude. So this ratio between the amplitudes of radial velocity tells you what is the mass ratio of the system. And let me just remember, if I go in here just to show you, we have this guy LB1 over here. And the core problem in here is that a star with these properties can be matched, for instance, by about a 4 solar mass main sequence star, or after it has been stripped during this contracting state, it is instead a much lower mass star, even potentially below a solar mass. So that means that the mass in here that was estimated for this H-alpha emission was far, far higher than it actually is, because the mass of the star was estimated incorrectly. So the way this unfolded involved quite a bit of steps. So first, it was pointed out that the way the RV data is taken from the emission lines could be very spurious. It could lead to significant errors. Then there was Andrea Eger in 2020 that pointed out that this B-type star is not just a vanilla B-type star. It has a very low surface gravity, which indicates that it has much lower mass than expected. I would say the final nail in the coffin was coming from Tomer Shenar, who did a bunch, like taking multiple spectra from multiple times, doing what's called spectral disentangling to actually separate both components. and found out that this component that has the H alpha emission, if you see it fully, it just looks like a regular B star. So this is just showing this disentangled spectra, that's the blue line, and comparing it to just regular B stars that we know, and it looks pretty much exactly the same. So this essentially was very clear that this is a system. It's in this new stage that's contracting, and given this confusion that they thought it was a black hole, that it ended up being one of these other systems, they ended up receiving the name of impostors. I guess that's what was being used at the beginning. I think it's losing favor a bit because now people are seeing them and recognizing them more immediately, that they're not just black holes, that they need to account for these binary effects. But then I guess another interesting one that we'll be talking about this briefly a bit more in detail. So this was another one. This is just a binary that's very close. This is less than 300 parsecs from the sun. And in here, they measured something that the solution they ended up claiming was that you have a star, a B star, with a black hole, and then a B star far out. So it was a triple system they were proposing for this. Again, there were reasons to end up with this, but I guess it all boiled down to not thinking that the B-type star could actually be a strip star, so one of these imposters. So just moving forward, what happened in the end? Turned out to be a B star. So this was, again, work that I worked together with Julia Bodensteiner to get this out. We're pretty much about the same time with Karim over here. We were more or less working on these very similar things, and I guess we ended up getting the name of black hole police at some point, just because black holes were being killed all the way around. So nice thing. This was further confirmed since it's so close by, you could actually observe it with VLPI gravity and see both components and confirm that indeed the solution that this is just a B star and a strip star that has a very low mass was verified. And there have been many more of this system. So Jaime as well has his own to his name, but they're accumulating as people realize this can be quite common. So why do I like these systems? I like them because they're an immediate snapshot to what happened after mass transfer. We have the mass transfer finishes. These stars are contracting to become very hot stars. And then we can know immediately after this mass transfer phase, what are the properties that were left over. So we can try and constrain more in-depth theories of binary evolution and binary interaction. Something quite interesting. So usually people were thinking that this would be a very quick thermal relaxation phase. So it would be very hard to observe in populations, but modeling them in more detail, more or less various researchers, so here's Duta and Klenki, did a large population synthesis, started realizing that they are actually very close to thermal equilibrium. So they have long lifetimes. Well, not that long, but they can still account for about 1% of what look like main sequence stars. So if you go out, observe 100 main sequence stars, you will end up with one of these. And with the kind of scales we talk about service today, this is a lot. This is something to worry about and to take into account. Okay, so I want to talk a bit then about constraints of mass transfer, how some of the systems can help us say, answer questions or give us worse questions to answer out of this. So I was talking a bit that we don't know how efficient mass transfer is. So mass goes from one star to the other one. We don't know how much mass is retained. And a very important part of that is that it's very easy for a star to be spun up to critical rotation. So if we have a Keplerian disk and material is fed through a Keplerian disk into a star, the angular momentum per unit mass that's coming is much higher than that of the star. And just by accreting a few % of its mass, we can go all the way down up to critical. So there are kind of two camps as to what happens when this limit is reached. One is that, well, the star is rotating at critical rotation. It cannot accept anything at this stage. So then we would say that mass transfer becomes very highly non-conservative after possibly just transferring a few % of its total mass. The other camp is that, well, we have an actual accretion disk, and what accretion disks like to do is transport angular momentum outward, transport mass inward. So possibly this is a way in which we can keep pushing matter into the star without feeding too much angular momentum, and mass transfer could remain mostly conservative. Now, I want to point out again this system HR6819, which I think it's quite interesting to try this out, because the mass ratio that was inferred from it, from this work I was saying by Julia Bodensteiner, is that it's about a mass ratio of 15 plus minus 3. So initially, this trip star was the more massive star in the system. But after all this process ended, all this mass transfer phase finished, it's less than 10 times as massive as its companion. So I showed you before these expressions to model orbital evolution. We can just account for conservation of angular momentum, and we get this kind of curves for, we can also do it for period as a function of the mass ratio. And now what we have is essentially, we have information in here about this end stage in here. So we know what's the period, we know what is the mass ratio, and we can work these relationships backwards and try to understand what were the progenitors of the systems. And if we do that, we need to go back, all the way down to a mass ratio before inversion. We find that the kind of periods that we predict for these extreme mass ratios before interaction are really not consistent with populations of binary stars we observe, that they're too short. It's really hard to get to this point. So what I tried to do within this work as well, that was trying to see, okay, what happens if there's an error in the mass ratio? So let's take like the lower limit within this uncertainty. So then that ameliorates a bit the situation. You don't get those extreme periods, and we can find some solutions that end up matching the final mass ratio. So that kind of works better for us. What we could say from here is that this is very likely very close to conservative, because if we see the tracks of non-conservative mass transfer, those are the dashed lines, they go far too low, and we would have expected anything to become a merger all the way earlier on. Now, this was kind of a nice result. So we have very strong indications of conservative mass transfer, but then more data comes and it makes the questions a bit harder to answer. So as I was saying, we have astrometric observations of this, and actually they did a lot of follow-up to actually track the entire orbit. This is observations with VLTI gravity. That gives us a relative astrometry, not absolute astrometry, but combined with the radial velocity information, this gives us everything we would wish about the system. So what happens when this is done? The mass ratio actually increased a bit, and the uncertainty narrowed significantly. So if we go back to how that plot looks, this is work being done by a student of mine, Ana Pico. We have here the lighter color indicates the old observation and its uncertainty. The darker purple color indicates what's coming out now. So we're really getting to a point where it's very hard to explain the system through our standard binary evolution formation scenarios. So Ana went a bit more in detail and essentially tried to model, like really say, okay, if we don't believe this mass ratio, and we think, okay, actually the true mass ratio of the system is lower, can we reproduce the system at different values for this efficiency of mass transfer, how much mass is transferred? And what we get out of that is something like this. So we're plotting in here this target mass ratio, what we would say the mass ratio is actually of the system, and how conservative mass transfer is. So one means we're fully conservative. We cannot go beyond that. We cannot create matter in our binary system. We can play with different total masses for the system, but overall the picture that we get is that as we consider that the mass ratio is indeed more and more extreme, we essentially can reject a large fraction of this parameter space, everything that lives in here, and we can only get 100% conservative mass transfer to produce anything. But the real solution leads further to the right. It's around 15. So we're finding a situation where even conservative mass transfer is unable to explain this extreme mass ratio. So this is something that in general interests me quite a bit, because we're finding these extreme systems. They're quite nearby from us, so there should be multiple more. So I expect these samples to grow a lot and tell us some things that we could not constrain before. Now I want to put up one extra comment on this guy that's over there. There's a single star that's more or less conspicuously hiding, which is called the quasi-Wolf-Rayet. So what is this guy? Why is it called like that? So this is the spectra of the quasi-Wolf-Rayet. It looks like a typical Wolf-Rayet spectrum. It has broad emission lines, also significant variability in some of them. The quasi part comes because the width of these lines corresponds to velocity variations that are on the order of 100 kilometers per second, while Wolf-Rayet stars are widths of about thousands or so. This one also has this funny bunch of lines in here, complex of carbon and nitrogen lines, which are referred to as the OF*P phenomenon. And it's normally associated to stars we know that are magnetic. So what was known about the system before? So for quite a while, there was what they had identified from the system is that there's a 1.6-day period variation in it that it's also observing in spectroscopy. So the assumption is that this is actually a system composed of a B-type star with something we don't understand in an orbit of 1.6 days. So more or less in work that was led by Pablo Marchant, we wanted to know, okay, what's the nature of this? Is this really some magnetic features that we're seeing here? And is this, how can we explain this in an evolutionary scenario? We have this trip star that looks very funny, living among all the others. So again, there was two things that came into this. One was some radial velocity analysis, or well, I guess I'm going to start with the magnetic field. There were some spectropolarimetric observations done of the system that confirmed that, yes, this is a magnetic star. It's actually 43 kilogauss, which is like the highest magnetic field you see of a non-degenerate star, like across the entire surface of it. But then more importantly, they did again radial velocity analysis, just with a few points. And then it was seen that these radial velocities, they exhibit large variations across short timescales. But if you average over them, we end up seeing that there is evolution, there is periodic evolution, but the orbital period is actually 8,200 days rather than 1.6. So the 1.6 period oscillation is just just pulsations that are happening on the B-type star. It's a very different phenomenon. Now this opens up some interesting questions because we have that the B-star component, we can estimate its age. It's too far out to have interacted with this object, and it's about 100 megayears. The strip star has about 2 solar masses, and more or less it shouldn't have interacted with this other guy. So the two questions here are, how can a star that forms a 2 solar mass core strip itself? That's one. And the other one is that a star that's massive enough to form a 2 solar mass helium core would be dead by 100 megayears. So how do we work this out? What can we do with this? And for this, just more or less what I thought about is that the system was actually initially a triple system. So we had the B-type star that we're seeing now is very far out, while the other two stars were initially in a few-day period orbit, similar to the systems I've been discussing before. So in this scenario, we have what's shown here in the HR diagram. We have a primary star that interacts with the main sequence, transfers a lot of mass, which lowers it in luminosity, while the other star increases in luminosity as a consequence, until eventually the primary becomes fully stripped and becomes a hot helium star. However, what happens in here is that due to pushing the mass ratio to such extreme, the accreting star can evolve very fast now, and it eventually catches up with the evolution before the other star depletes helium. It terminates its own main sequence and expands and initiates a phase of inverse mass transfer. What's interesting in this kind of scenario, which is pretty much generically expected for systems like HR6819 and these other impostors, is that mass transfer should be very highly unstable in this case. The mass ratio is very extreme. We should have very strong orbital shortening as a consequence of mass transfer, leading to dynamical evolution. So what we are saying is that if there's a merger in this case, the two cores of these stars, these helium cores, can merge, form a more massive helium core while ejecting these hydrogen-rich layers. So this gives us something that matches the properties of the quasi-Wolf-Rayet star. It matches as well the age of constraint from the outer B star, and also gives us a reason, a way in which to produce these very strong magnetic fields. So this is like a very funny scenario, but as we've been exploring it further, it seems that it can actually be quite common. It's not this very weird thing, and it probably contributes significantly to the population of strip stars. So you can think about this as some sort of helium struggler, essentially. Helium stars that would live in a population being more massive than the ones you'd normally expect. Okay, so in more or less not much time that I have left, I just want to put some brief comments about the future, interesting things I like that more or less I'm working on, and things that I think are going to happen. Cannot be very comprehensive, but the first one I want to talk is that most of the simulations I was showing you that I do myself are in one dimension. But I think for many problems, like this problem on how conservative mass transfer is, if we want to deal with it from first principles, we need to work with 3D simulations. So this is some work that was done by David Dixon during his PhD. He's a postdoc that just started at KU Leuven that I'm collaborating with, and he was trying to model an X-ray binary. So this is M33X7 that's potentially undergoing a very strong phase of roche-lobe overflow. So it's capable of putting a star. This is more or less the way the star was constructed in this case is a bit simplified, not being fed from a detailed stellar evolution model, but he's able to trace essentially the formation of this accretion stream, this accretion disk, and mold step by step how the star would keep evolving and overflowing more and more and more and more. So this is more or less a mixture of 3D simulations and some approximations on how the binary evolves. Now, what we want to do in here, what we're working on is actually feeding detailed stellar structures data into this. So we can actually do the 3D simulations, but for the deeper interior of the stars, we use 1D techniques that we can cover this longer timescale evolution. So for that purpose, we're using the work of a former PhD student of mine, Matthias Fabry, where essentially what he showed, and it's something that's often done for rotating stars, but in this case, we're doing it for binaries in full 3D, is that if we think in a different way, if rather than thinking of radial shells, we think of constant equipotential surfaces of the Roche potential, we can cast the equations of stellar structure in a one-dimensional form while still capturing the 3D structure. This is there are some simplifying assumptions, but what we get when we run a stellar structure code in this way is something that we can map into 3 dimensions. So what is the status of this? Well, we've produced some binaries, and I guess the outcome looks a bit like this. So what we're showing in here, we have 2 cases. We have a system where there's overflowing material. There's a system where there's underflowing material. What we're trying to check for the moment is just that the initial conditions make sense. That's our starting point. So we can see that as a function of the gravitational potential, we have the density that comes from our stellar evolution model. We have the initial condition in blue, and more or less after a bunch of relaxation had happened, we have the orange points marking the structure of the star. And what we find on the left is really just a boring case. I guess the colors might not help too much, but the thing is that these 2 overlap. So we put a detached binary, the binary does not start exploding or doing anything insane. It's just boring detached binary. On the other hand, there's a lot more stuff to swallow. That's a system that undergoes overflow. So there's a lot of stuff happening, material that's moving to lower potential regions at much lower densities. But we also find that in the deeper layers of the star, we are preserving our 1D structure. So we can possibly do this step between jumping between 1D simulations to these full-on 3D simulations. Other thing that I think is very interesting is the production of better population models. So I've been showing you cases of single systems that can give us insight, but in practice, we need to be able to explain full sterile populations with whatever theory we have. This has been dominated for the most part with these rapid evolution methods that I briefly mentioned, but now we're having more and more people adopting detailed stellar structure calculations that are heavy. They are hard to compute and get, but they give us very important feedback that we need. So this is just a simulation by Jan Henneko, a former PhD student at HITS that's trying to cover this. And it's really one really needs to try and map all the input parameter space of binary stars. That's what makes this hard. We need to cover different orbital separations, different mass ratios, different donor masses, and then run a full simulation for each of those. This is something I'm also investing a lot of time for my ERC project. It's called Stargrass. We're trying to create new tools to do stellar evolution, doing a new stellar evolution code that's very well tailored for this kind of calculations to do them efficiently and reliable. Next, I want to just do two final things on some surveys that I think are important. The Bloom collaboration that I'm involved in has observed with VLT flames about 1,000 massive stars in the Small Magellanic Cloud. Interestingly, it has also observed them 25 times. Well, not yet 25 times, but that's the idea, that we have 25 epochs of about 1,000 massive stars. And this will really be excellent to constrain properties of the binary systems in here. It's really designed from the beginning to target this as a science problem, science objective. And I'm very excited to see what will come out of it. And a bit more on a longer term, something that I do want to see happening in the future. This is the UVEX mission. It's a mission led by NASA, and people are Caltech at Berkeley mainly, but there's a large international collaboration. And this is about a 70 centimeter telescope. It's not something gigantic, but it's gonna allow for a very large improvement on surveys in the near UV and the far UV. So this will play an enormous role in terms of understanding strip stars in general that are very hot and hard to detect. And just to finish, want to point you out that a lot of the things I said today can be found in my review on the evolution of massive binary stars with Julia Borensteiner. And I'll just leave you with some takeaway messages. Thank you very much.
Thank you very much, Pablo. I think we'll open questions. Student questions. So if anybody wants to kick off. And while we're waiting, if I could ask Navinal just to check online if there are any questions online. Okay, not at the moment. Well, I don't see anything, so there's one in front. Thank you. Excellent.
Hi, Pablo. It's just an understanding question about the HR6819 system. You said Ana Chiara shows that it's difficult to produce the high mass ratio even with a conservative mass transfer. Was the solution to that you have probably it had case A mass transfer already on the main sequence, or what are your thoughts on how that system formed then?
So well, the models that she's doing actually end up doing mass transfer in the main sequence.
Okay.
So that's kind of, and it's also generally, if you interact during the main sequence, you haven't formed your helium core by then. So you can actually lower the mass of the star and produce a less massive helium core by the end. So that pushes the mass ratio to extremes, but it's still not enough.
It's still not, okay.
It's still not enough. That's what we're finding.
Thanks. Yep.
So I was wondering, what are the parameters or the assumptions that go into your evolutionary models that could change the outcome of the evolution of this particular system? Have you played, for example, with overshooting?
Yes, so we've tried in a sense, if one uses lower overshooting, you can produce smaller helium cores, and that also allows you to push a bit further. And that moves us from 11.5 to 12.5, kind of. So it's still quite far off. And I think it's also fair to still think if you shouldn't often do that and question the observations. But I think that there are other details about this system that make it sound like there could possibly be something off in the observations, like the luminosities of the stars are also a bit far. They're too high for the masses that are being reported. And that's something that's very hard to explain. But at least we played a bit on the theory side to just see, okay, let's trust the observations. Can we get this mass ratio? And we don't have any good ideas on how to do so.
Okay, question.
Hi, thanks for the talk. I'm interested in the quasi-Wolf-Rayet stars, if I understood, or a single star. If I understood correctly, they are not genuine Wolf-Rayet stars in terms of initial mass, stellar feedback, stellar wings.
The what star?
The quasi-Wolf-Rayet stars?
The quasi-Wolf-Rayet, I mean, it has this category, but this is the quasi-Wolf-Rayet star.
Yes.
This is the only one.
Yeah, the only one. So it's not a true Wolf-Rayet star in terms of the initial mass and stellar wings.
No, so if we put it back here, so if we see where it's living, the Wolf-Rayet stars are all the way up here.
Yeah, exactly.
So this is very far down. So
Small in mass.
so yeah, in the end, these emission features are actually expected when you have strong magnetism. So what can happen in that case is that you have a weak wind that usually wouldn't produce emission features, but that it's funneled by the magnetic field of the star and can essentially form whenever the magnetic field lines go together, it can form high density regions that are capable of forming emission features. So that's the expectation, the explanation for the spectroscopic nature of the star.
I see. And what's the fraction of it? What's the intrinsic fraction in the universe? Do you expect it to contaminate the Wolf-Rayet population?
So we're still working on that, but what I can say, so if you want to talk about a fraction, you need to do full population synthesis and compare everything to everything. What we've been doing is doing simulations covering a broad parameter space. So what I can say is within the parameter space of initial condition, what fraction of systems would end up undergoing this compared to others that would not. And I expect it to be above 10% that go through this rather than just a regular vanilla stripping stage. Yeah. Don't quote me on this number because we still need to compute it quite quickly. This is just me integrating by eye some of the plots we have.
Hi, Pablo. Thanks a lot for this.
Well, I think these ones are at lower metallicities because the candidates were constructed from a catalog from the LMC and the SMC.
And do we find those in the Milky Way?
In principle, they should be around, but I guess it's harder to have a very concentrated region where you would have a UV survey to go through the same process. So I guess that's the main thing. It's just the Magellanic Clouds are very convenient. They're very compact. They have a lot of stars. They have a very well-defined line of sight, so we don't need to care about extinction so much as we do in some places of the galaxy. So yeah, but indeed, there is a bit of a gap as well. If you talk about the range that goes from here to here, I have some ideas about that, but I wouldn't venture saying them out loud yet.
Okay, well, we thank you for showing us a lot of the ongoing work. I think this question of additional ionizing radiation from all these strange populations of stars is going to be a number which I guess is going to be important for understanding galaxy evolution as well. So I think we are getting towards the end of the time. Are there any questions online? Nothing online. Then, if I may, I'd just like to ask Amy if there is any announcement about dinner, if you would like to actually say something about that. And any other meetings?
Well, I already contacted people that that wrote me to join dinner, so you should have the information for this. If you didn't, probably we won't have much more space though, because we already booked the table. But maybe you can join for drinks before dinner or after. I don't know. Oh no, drinks. No, drinks. We're going to go directly from here with the students. Okay, so let's meet outside, right?
So, anybody want to, students wanting to join, just meet up with Jamie, and also for dinner as well, and then you'll get the message. Okay, well, with that, I think we must thank you, Pablo, very much for this extremely interesting and pedagogical introduction or, well, commentary on this very complex situation. And I'm sure that we'll see a lot more in the future as you develop your work further. Thank you very much.